Chapter 3, stoichiometry. So I'm going to be moving pretty fast. Stoichiometry is simply well, it's from the German, which means, actually, I don't know German. Anybody know German? No, okay. Let's just go, that's where it came from. It was coined by a German, but what it means is to, it's kind of a budget of a reaction. Now, prior to the late 19th century, chemists all thought that reactions were just mass and mass, like Lavoisier said, mass in, mass out. But that is not what is happening during a reaction. During a reaction, you're getting individual atoms and molecules interacting. And they have different masses. So if you just follow the mass, you're never going to get to the root of what's happening in a reaction. That's why up until the Karlsruhe Conference in 1865, when something went wrong in a university scientist research project or in a company that's manufacturing product to make money off of it, and they were losing their shirts because their reactions went wonky and they didn't know why. It's because they were all based, their logic, their thinking was on mass, and it should have been on atoms and molecules. That's where Avogadro, that's where Avogadro and his student Cannizzaro come in and solve the problem for them. So stoichiometry is a method for following the quantities of material that go into the reaction, the quantities that come out. Now, you may say, we're going to put the mass of this together, and we get products of certain mass. But in order to follow the progress and account for the movement of those masses, you have to convert all your masses into numbers of atoms and molecules. And that's what we're going to head toward with stoichiometry. Okay. First thing we have to do, since atoms and molecules are too small to see, we can't actually count them. It'd be nice if we could, but we can't. So we devise a method to count them by weighing. In order to know how many we've got by weighing, we have to know what's the average mass of each of the atoms or molecules that we're weighing. If we know the average mass of each one, then we can use a conversion and find out how many there are. So that's where dimensional analysis comes in. Unit conversions. Okay. Yeah, atoms are too small to count. We also have to assume that all the objects in our group that we're counting by weighing are essentially identical. We know they're not, but for our purposes, we take an average value for each one. Okay, so here's our example. We have a pile of marbles that weighs 394.8 grams. A pile or a jar of marbles, that would be better. Pile of marbles is not going to stay put. If you want to find out the average mass, and you don't want to count every marble in the jar, you just take 10 of them out. Representative 10 marbles and weigh them. So we can find out the average mass of a marble simply by ratioing 37.6 grams to 10 marbles. Okay. Now we know that the average mass of our marbles is 3.76 grams per marble. Now, if we resampled them, took out 10 more, it might be slightly different because all measurements have error, right? We learned that early on. And sometimes that's what we have to do. We have to sample and resample and sample and resample, like J.J. Thomson did with his electrons, just thousands of times. But for our purpose here, we're going to assume that one marble has a mass of 3.76 grams. Now, if we know the mass of all of the marbles is 394.80 grams, that's the total. then now we have a conversion factor because we know that 10 marbles equals 37.6 grams, or one marble equals 3.76 grams. So we can get rid of the grams in the numerator here, denominator here, marbles here. We have one here, and we found that it's 3.76 grams. Just divide that in there. That one cancels, leaves us with marbles. And that should be 105. That's our best estimate for the number of marbles in that jar. We might be off by 1, plus or minus 1. So what we do with atoms, we need a way to determine what's the average mass of an atom, so that when we weigh a pile of I don't know, oxygen atoms, or weigh a pile of phosphorus atoms, if we know the average weight of each atom, then we can use that conversion to find out how many atoms there are in the pile. So what we've done is we just picked a standard element. By the time this method was developed, we knew about isotopes, right? So if we're going to pick a standard mass for an atom, we have to be particular about the isotope. Originally, they used oxygen because most of the metals in the Earth's crust are bound with oxygens. But that didn't work out too well because oxygen's a gas. If you try to do oxygen by itself, it's difficult to handle. We needed something that is a solid. Easy to find, easy to purify, easy to split, to divide apart into its isotopes. And that turned out to be carbon. So our standard is carbon 12, that isotope. And it is arbitrarily fixed at 12.000 infinity. Atomic mass units. One atom is 12 atomic mass units. Okay. So this is the only isotope where its individual atomic mass is the same as its mass number. 6 protons and 6 neutrons. The rest of them are going to be fractional because they're based upon that carbon. In fact, other isotopes of carbon are going to be fractional also.
So is that AMU percent? Is it really small? Is that a really small?
Yes. Yeah. You can assume that one atomic mass unit is roughly the size of one proton. Okay, there's our standard. Now, this textbook that I'm using for the slides uses U for atomic mass units. I don't like that because it's easy to mistake that for the Greek letter, like that. So I use AMUs just to be particular. I'm not sure about Brown. I haven't looked at Brown in a while, whether they use U's or AMUs. Okay, everything else is based upon that standard. Now, the way that they ratio one to another, it would take a whole semester to get a handle on it. So we're just going to have to take their word for it. All right, in nature, carbon is composed of 98.89% carbon-12. The next major isotope is carbon-13. So it has one extra neutron, but it's only 1.11%. And that, if you add those up, that's 100%, because the other isotopes of carbon are just vanishingly small. Carbon-14 is like 0.01%. Yeah. And besides, carbon-14 is radioactive. So you might measure it one day, and a month or two later, it'll be less, be converted into something else. So for for convenience, for chemists, this is what physicists do or physical chemists do. For chemists, everyday bench chemists, we just need to know what is the average, weighted average mass for carbon if we isolate carbon from nature. From a living source is usually a good place. You just burn it and separate the carbon from the ash. Or you burn it and get the carbon dioxide, separate that, and get the carbon out of it. So all we need to know is what's the average atomic mass units for a carbon atom in naturally occurring. We don't want to deal with isotopes because we don't have the equipment to do it. So this is how the values that are in the table, in that table, it's the upper left-hand corner. It's the atomic mass. That's different from the mass number. Mass numbers are always whole numbers because they're protons plus neutrons. But the atomic mass is a weighted average of all of the masses of the isotopes. So we do this kind of like calculating your grade point average. Right? If you have, this class is 4 credits, right? So let's be optimistic. Say you make an A in this class. That's 4 times 4 is 16 value credit units. And then if you make, if you have another course, it's 3 credit units, you don't do so well, maybe it's C. So that's 3 times 2 is 6. So 6 and 16 is 22, right? 7 into 22 gives you your weighted average, grade point average, okay? So the way we work it with atoms is we say this isotope is 98.89%, and the fractional equivalent of that is 0.9889 times 12. That's the contribution of that isotope to the average. The contribution from carbon-13 is 13.0034 atomic mass units for that isotope times its abundance, right? 1.11% is 0.0111 fraction. Multiply those together and then add them up. That gives you the contribution of each one. Okay. Well, if you calculate them out and then add them together, you get 12.01. Rounded off to 2 decimal places. 2 decimal places is good enough for us for 2 reasons. One is we're not doing research to publish in a referee journal. And the other reason is 2 decimal places is going to be the same now forever. Because every time we come out with a new periodic table and we get analytical work from chemists and physicists that do this, nothing else but this all their lives, the values are only going to change in about the 5th or 6th decimal place. So if we stick to 2 decimals, then we can use that same periodic table forever. Okay. Now here's sort of a trick question, just to see if you understand what we've been saying. If we take a sample of carbon from nature and we clean it up so there's nothing but carbon there, now we start dividing it into groups. And we take this one and have it, and we keep having till we get down to 2 atoms, split them apart, we got hold of 1 atom. What's the probability, or what are the chances that that atom is going to weigh 12.01 atomic mass units?
Very low.
Yeah, it's 0. You're never going to get 12.01 atomic mass units for 1 atom because it's a mathematical average. Okay? It's either going to be an isotope 12 or it's going to be an isotope 13.0034 or something. It's never going to be 12.01. That's an average value so that we don't have to separate the isotopes and do the averaging ourselves. Right? We'd spend all our time doing that instead of chemistry. All right. I'm going to abbreviate this as short as I can. This is how we separate isotopes. It's called a mass spectrometer. All you have to do is take your sample, say we have pure carbon, and you take your sample, it's a mixture of isotopes. You run it through an electron beam, which knocks electrons off of it and gives you positive ions. Okay, so you're going to have this one is going to be a positive charge, and say this one's going to be a positive charge. And then you have some others. Then you, the electron beam is negatively charged, and those plates are positively charged. Excuse me. No, that can't be. They have to be negatively charged so they can accelerate the carbon through them. They're negatively charged. We accelerate the carbon atoms through those two plates, and the plates are aligned so that nothing can go through like this. It shows that they do, but not really. They come through in a straight beam. It's called collimation. We're straightening. The only ones that get through are the ones that are in a straight line between these two holes, two slits, right? Once they get through there and they're moving fast, we run them through a magnetic field. Now, the way this is oriented is wrong. If they're going to bend this way, the magnetic field has to be that direction. Magnetic fields bend ions perpendicular to the field. But, you know, the artist here probably wasn't a chemist or a physicist. Anyway, what they do is when they go through that magnetic field and they bend, they're all traveling at the same velocity, right? Because of the same charge accelerating through the same electric field. So this one has picked up more energy because it's more massive, but it's traveling at the same speed. So when it goes to that field, which one's going to bend more? The lighter one. The lighter one's going to bend more. So up there at the top is going to be your carbon 12 relative to carbon 13, and carbon 13 is going to be down here. And we have detectors now with computer programs that will count individual strikes, individual atoms. They're that fast. So you just count the number of strikes at your calibrated position on your detector and then ratio them. And that tells you that you have 98.89% carbon 12. All right, I wasn't going to talk that long, but couldn't help myself. All right. So here's an example of calculating the average atomic mass for this element. We don't know what the element is yet. 62.6% of 186.956. Let's see, do I have it animated? Yeah. So we use 0.626 times 186.956 and 0.374 times 184.953. So the average atomic mass with those two isotopes in the mix is 186.2 atomic mass units. Okay. What's the element? We've learned how to find the element with the atomic number, but we don't have the atomic number. Fortunately, as we add protons, we get more massive too. So the atomic mass is almost as unique as the number of protons. So you can just work your way down from left to right, top to bottom, until you find 186.2 if it's, or close. And I can't see from here. Can you see which one it is?
The LU is like 174. So that's 7.
That's not big enough. Keep going. Okay.
Maybe key.
Here, I see it. This one's pretty close, 186.207. That's rhenium. Okay, RE, rhenium. You didn't have to memorize that one, so don't worry about it. All right. So when we're counting atoms, molecules, ions, in order to get a weight that we can measure on any of our balances, we need lots of them. You know, billions and trillions and quadrillions of atoms, because they're so small and each one weighs such a little amount. We have to gather a whole bunch of them together to get something we can weigh. So we need a new unit, and that unit is the mole. The mole is simply a number of things. Now, it didn't spring full out of somebody's head. It's based upon actual physical properties, and it's recalculated from time to time to the fifth or sixth or seventh decimal, right? So we don't have to worry about it. We can use the number I'm going to give you and just go with it. Right? But by definition, the mole is the number of carbon atoms in exactly 12 grams of carbon-12 isotope. That's our peg. That's what holds it in place. So if we have 12 grams of pure 12 carbon-12, we have exactly 1 mole of carbon atoms. Right? Everything else, again, is based upon that. So what is that value? It happens to be 6.022 times 10 to the 23rd atoms. Or things, actually. Once we figure out what the number is for the atoms of carbon-12, then you can have a mole of anything. You can have a mole of atoms, you can have a mole of ions, you can have a mole of molecules, mole of water molecules, for instance, or a mole of formula units of sodium chloride. Right? Now, the nice thing about that number is coming up. 1 mole of naturally occurring carbon with its mix of isotopes. 1 mole is exactly 12.01 grams. So 12.01 atomic mass units is the average atomic mass for that mix of atoms, or our average carbon atom. But if you have a mole of that mix, that natural mix, you will have 12.01 grams. So the nice thing about that is, on that table, when you see those fractional values in the upper left-hand corner of each square, that can be an average atomic mass unit for the atom, or it can be the mass of a mole of those atoms. That's the more useful value. So for nitrogen, if we take the average value of nitrogen to 2 decimal places, it's that. Now that could be atomic mass units per atom. It's also grams per mole of nitrogen. Okay. That's going to be extremely valuable when we start doing stoichiometry in chemical reactions. All right. So what's the number of atoms in 4.48 moles? Okay, we start with 4.48 moles, and we want the number of atoms. Okay. 4.48 moles, and we want to convert that somehow into atoms. So we need to get rid of moles, right, numerator, denominator, and leave us with atoms. So when you see that ratio, you know that 1 mole is 6.022 times 10 to the 23rd atoms, and they're your conversion factor. Just multiply it out. And you should get 2.70 times 10 to the 24th iron atoms. Okay? That value, 12.01 grams per mole, is called molar mass. So nitrogen, oh, I was wrong. It wasn't 14, it's 14.01 nitrogen. Sorry. Rounded off to 2 decimal places. Now, how about the molar mass of a compound? Very simple. In this compound of water, how many moles of hydrogen do we have? Well, we've got a hydrogen here, and an oxygen, right? So the molar mass of water is 1.01 grams per mole for that hydrogen, 1.01 grams per mole for that hydrogen, and 16 grams per mole for that oxygen. So the total is 1802 grams per mole. If we have a mole of water molecules, they will have a mass of 18.02 grams. You just add up molar mass for each of the atoms. If you have multiple atoms, just multiply the value times whatever, and just add them up. So water is 18.02. Coming up is a bigger one. Barium nitrate. Barium is a big, huge atom. It's in the second column, and its mass is 137.33 grams per mole. Now, they left out the mole in this animation, or I left out the mole, but it's grams per mole. We got 1 mole of barium, which is 137.33 grams. We got 2 nitrogens, right? Because they're inside that parentheses. And we have 6 oxygens, 6 times 16. Then you add them all up. And the molar mass of that compound, that formula, is 261.35 grams per mole. Okay. All right, this is a trick question. Which of the following is closest to the average mass of 1 atom of copper? We know that there's no atom of copper that's going to weigh 60 grams. Right? That's impossible. So E has to be the answer. There's no way the others can be. But if we did the calculation, 1 copper atom, then we convert copper atoms to moles, right? Moles on top, atoms on the bottom. Divide 6.02 times 10 to the 23rd into 1, gives you a very small number. Then the average mass, 63.55 grams of copper for every mole of copper. That cancels the moles and gives you grams. And that value will be 1.055 times 10 to the minus 22 grams for 1 atom. How many copper atoms are in 63.55 grams of copper? If you look up there, you find that's the molar mass. Got 1 mole, which is 6.022 times 10 to the 23rd atoms. Will give you that mass because it's equal to 1 mole. All right. If you have a 100-gram sample containing magnesium, zinc, silver, yep, silver. You got 100 grams each. Which one has the greatest number of atoms? If they're all the same mass, and each atom has a different mass, then the one that's going to have the highest number, the greatest number of atoms, is the one that weighs the least amount, because it takes more of them to make 100 grams. So all we need to do is find out what's the mass of each one. Magnesium. I need to get a closer chart. Here we go. Yeah, magnesium, 24.31 grams per mole. Zinc, we did copper, we didn't do zinc. Zinc, 65.39. And silver. Silver is a bigger atom. 107,887. Okay. So silver is actually going to be less than a mole to give 100 grams. It's going to take more than a mole to give you 100 grams of zinc, and even much, much more magnesium, because each one has less mass. So this one's going to have the greatest number of atoms. There. If they all have the same mass, the smallest one will give you the greatest number of atoms. Okay. So now we're going to muddy the water some. Let's say we have zinc, silver, and magnesium again, only now we have different masses of each one. So 107.9 grams of silver and 70 grams of zinc and 21 grams of magnesium. If we're going to put them in order of greatest to least number of atoms, we can go in and calculate, just use the molar mass and calculate. Right? But if you're in a hurry on a test and you just want to put them in order, just find out what's their relationship to the moles. How many moles of each one, right? It may work and it may not. So silver was what? Let's look at silver again. Silver is 107.87. 107.8, that's 1 mole. Okay. Zinc is 65.39. That's more than a mole. And 21 magnesium, magnesium is about 24. This is less than a mole. So good. We've only got 3, and we've got equal to, greater than, or less than. If we're going from greatest to least, so this is less than a mole. Next is a mole. And next is greater than a mole. That will be in order. Zinc, silver, magnesium. Wait a minute. Greatest to least? That doesn't look right. Zinc is greater than 1 mole. Yes. Magnesium is less than a mole. Oh, it went backwards. Okay. I went backwards. It should be that way, that way, that way. Right? Yeah. I wrote them up there backwards. All right. If we have a 100-gram sample of each of the following: water, nitrous oxide, propionic acid, and carbon dioxide, and we want to rank them from greatest to least number of oxygen atoms, then here I'm going to invoke Henry Ford, set up an assembly line. So if we have water, let's move it over here. Nitrous oxide, that's the old way, nitrous oxide. Should be dinitrogen monoxide by the modern nomenclature. But I like nitrous oxide because it invokes laughing gas. All the dentists have it in their office. C3H6O2, O2, and carbon dioxide. Okay, if we want to know greatest to least number of oxygen atoms, we don't actually have to find out how many atoms. We find out how many moles. That's the counting number. That works. So in order to do that, we need to find out how many moles of the molecule and then ratio the number of oxygen atoms in each one. As if we have 1 mole of water, we got 1 mole of oxygen. We have 1 mole of propionic acid, we have 2 moles of oxygen. Right, so that's another conversion factor. So we've got 100 grams of each. Okay. I ought to get you guys to do some of my legwork. We need to cancel grams for each one and leave us with moles of compound. Right, moles of compound. So we need, whenever you see grams and moles in quotient, that's molar mass. So molar mass, we did water earlier. That's 18.02. Nitrous oxide. Okay, we got two nitrogens. 2 times 14.01 and then 16 for one oxygen. So we should be able to do that one. That's 2, that's a 0, that's a 6 is 14. And 1 and 3 is 4, 4402. Go. This one will take a little more legwork. 3 times 12.01 for carbon. Hydrogen is 1.01. Oxygen is 16. Okay. Add that one up. I'm not going to try to do that one on the board. Okay. 3 times 12.01. That's 3603, and then 6.06 for the hydrogens. And then 32 for the oxygens. That's 7409. And then carbon dioxide. That's 12.01 plus 32. Because 2 times 16. So that's 104. 4401. Okay. Now that gives us moles of compound. So once we got moles of compound, we want to cancel the compound and leave us with moles of oxygen. Oxygen compound, oxygen compound, oxygen compound. I left out the mole part. Forgive me for that. Okay, this is a 1-to-1 ratio. That's a 1-to-1 ratio. For every mole of compound, you have 1 mole of oxygen. This one is 2-to-1, 2-to-1, and this one's 2-to-1. So now we can calculate values. 18.02 divided in times 1 is 5.55. 5.55 moles of oxygen. And let's see. 100 again divided by 44.02. That's 2.27 moles of oxygen because this is 1-to-1. And then again, let's see. 7409 divided into 100 times 2. 2.70. And the last one, 44.01 times 2 is 4.54 moles of oxygen. Okay, put them in order. Greatest to least. So this is the greatest. This was the next one. This is the third one, and this is the fourth one. Okay. And I say Henry Ford because we did the calculation exactly the same each time. The only thing we did was change the tires. Or it's like, what did Henry Ford say about his Model T? You can have any color you want as long as it's black. Give him credit for the assembly line. He was a rabid anti-Semite and racist, but that aside, he did make some good cars.
Perfect, got the first card.
Yeah, probably. Yeah, because was it Benz?
Yeah.
Benz perfected the carburetor. Yeah. and named the company after his daughter, Mercedes. Okay, this is just problem-solving technique. What's the question? What information do you have? Do you need any other information? And plot your strategy for solution. Is it really simple? Just a couple of steps? Or do you have to bust it apart into pieces, solve those, and bring them back together? Right, those really complex ones do that. And then the last thing, don't forget to do this one, reality check. Does your answer make sense? Right? If you calculate the mass of an individual atom of copper and it comes out to 65.33 grams, there's something wrong with this picture. Okay, how do we express composition of compounds? All right, we're going to digress a little bit, but we need to know this. When a bench chemist goes into the lab and is given a compound to analyze, the results that he or she will produce are usually in mass percent. What's the mass percent of each element in the compound? That's what they'll give you. Which simply means the mass of the element divided by the mass of the compound times 100. It's that simple. Right? It's a dimensionless number. That's the problem with percent. It just means parts per 100. You have to know what the parts mean. Is it parts by mass? Is it parts by volume? Is it atom percent? Atoms for atoms? In this case, it's mass percent. Mass. Sometimes when we see it, if the publisher is conscientious, they'll say percent, mass. That means the value in the numerator is by mass and the value in the denominator is by mass. Or they may say mass per unit volume. Or they might say volume per unit volume. This is the one you see in the liquor store. Alcohol by volume. It's percent volume of ethanol in the total volume times 100. All right, let's back to the problem. Mass by percent by mass. Now, once we know the formula for the compound, we can calculate the theoretical value. All we have to do is say, let's assume we have 1 mole of that compound, Fe2O3, iron 3 oxide. If we have 1 mole of it, then we have 2 times the molar mass of iron, which would be what? Iron. Fe 5485. No, sorry. 5585. So we have 2 times 5585 grams per mole. And we also have oxygen. Total mass for 1 mole of the compound then would be 3 times oxygen, 16. Okay? So if we want to know what's the percent by mass of iron, we just say 1 mole of that compound weighs this much. In that compound, how much does the iron weigh? The iron weighs 2 times 55, 45. So that's the iron in the compound. This is the total compound based upon 1 mole times 100. Now we'll give you the theoretical percent by mass for that compound. There it is. 69.94% by mass is iron. So if we have 100-gram samples of each one of these, rank them from highest to lowest percent oxygen by mass. All right, that's going to take a lot of time. You just say, for instance, let's just do water. Right? Instead of ranking all of them, we'll just do water, and you can do the same for each one and compare them. So percent by mass for water would be what? For oxygen? Yes, percent oxygen. So how much oxygen is in that thing? For 1 mole, 1 oxygen is 16 grams. The total is 1 oxygen plus 2 hydrogens, right? Times 100. So we'll calculate that one just to be thorough. Did I do that right? Yeah, okay. Here we go. So it's 16 divided by 18.02 times 100. 88.79%. That's pretty high percent. And that's probably the one with the highest percent oxygen out of that group. And you should do the same thing for each one. And then you can rank them. There's what you should get. Water's the highest percent oxygen, then carbon dioxide, then propionic acid, then laughing gas. So now, we determine the percent by mass if we have the formula. But go back to the bench chemist who's given you percent by mass of the compound. How do you determine the formula from that information? That's what we're going to do next. So we went one way, now we're going to go the other way. Come back. And this is the first time you see it. I need to do this complete, but I need a definition first. There's a difference between the empirical formula and the molecular formula. And we use molecular formula loosely. It may not be a molecule. It could be a formula unit, like sodium chloride, calcium sulfate, an ionic compound. So molecular formula encompasses all of those. The empirical formula is the simplest whole number ratio of elements in the compound. So illustrate the point. If this is the simplest whole number ratio, for every 1 carbon, you have 1 hydrogen. That could have been the compound that gave us this value could have been acetylene. It has a ratio of 1 to 1. The empirical formula here, and if we use the multiplier, right, N equals 2. What if we change that multiplier to 6? Now we get C6H6, which could be benzene. Right? So you get 2 different molecules from the same empirical formula. If the question is, what's the empirical formula? You try to divide through to give you the simplest whole number ratio. This one you divide by 6, this one you divide by 2, and both of them would give you 1 to 1. That's the empirical formula. If you have the mass percent composition for a compound, you can calculate the empirical formula. Easy. In order to go to the molecular formula, you need the empirical formula, and then you need, by some other means, the actual molar mass for the compound. And I'll show you how that works in just a minute. This is what's known as a carbon water train. You push pure oxygen into your sample, you combust it, and it makes oxides. You absorb the water in some absorbents. In this case, it's magnesium perchlorate. It works really well. And then you get the carbon dioxide out with sodium hydroxide. Okay. All you have to do is take this one and weigh it before, and then run the experiment, weigh it after, and then you got a mass for the water. And you can find out from that mass how much of that mass is actually oxygen. So you get a mass for oxygen. Do the same thing for the other one, get the mass for carbon. And then if you have oxygen in your sample also, then and it's the only thing left, then you get oxygen by difference, what's left over. Because you can't analyze oxygen this way because you're pumping oxygen through there. All right, it works pretty well. I've done it in the lab. It looks real messy, but it works. Okay, so let's take this example and calculate both the empirical formula and the molecular formula for this compound, adipic acid. Adipic acid is a fatty acid, right? Anybody had anatomy and physiology? Okay, so you know what a true fat is. It's a triglyceride. You form an ester of 3 fatty acids and 1 glycerol molecule. Well, this is one of those fatty acids that could be there, adipic acid. All right, so what we're given is percent of carbon, hydrogen, oxygen, and that's it. We know that those are the only elements in this compound. 49.3% carbon. Oops, need to clean the slate here. 49.3% carbon, 6.9% hydrogen, and 43.8% oxygen. All right. So what we're after is the simplest whole number ratio of atoms in the formula, or moles. It doesn't matter. It works both ways. Right? If you get the mole ratio of each one in the compound, the simplest whole number value of that ratio is the empirical formula. So what's wrong with this picture? Percent is a dimensionless number. We can't convert it to moles, right? Because it's parts per 100, right? There's no grams in there to convert to moles. So what we have to do is make an assumption. Let's assume this ratio by mass is fixed, right? Remember, whose law was that?
The carbon fixed.
That's the one where no matter where you get your compound, it's always the same mass ratio of elements. I think it was Proust. Yeah. Anyway, so if we assume that we have 100 grams of sample, that means parts per 100. If this is percent by mass, then we know if we have 100 grams, we also have 49.3 grams of carbon. Now we can go somewhere with that. 6.9 grams of hydrogen and 43.8 grams. Now we can convert to moles. We just need to get rid of grams and leave us with moles. There's that quotient again, grams and moles. So carbon is 12.01 grams per mole, right? Hydrogen is 1.01 gram per mole. Oxygen is 16 to do decimal places. And that'll give us a ratio. All right, so 49.3, 12.01 divided into that is 4.105. 4.105 moles of carbon. And 6.9 divided by 1.01 is 6.832 moles of hydrogen. And oxygen, 43.8 grams divided by 16 is 2.738 moles of oxygen. Okay. We can't put that in a formula, right? You need a whole number ratio. Now, how do you get a whole number out of that? Now, this ratio is fixed. That is true. That many moles of oxygen, that many moles of hydrogen, that many moles of carbon. So if we do the same thing to each value, say we divide by the same number, we haven't changed the ratio. I mean, that's an axiom of math. So what I do is divide by the smallest one first, right? 2.7308. 2.738, excuse me. 2.738 and 2.738. And the ratio will be the same. That's 1, obviously. How about, let's see, flip this and divide by, oops. Here we go. 2.50, rounded off. Getting close. And 4.105 divided by 2.738 is 1.5. Okay, we're getting close. Now, what we have to do is multiply this by something that'll get rid of that 0.5. So how do you get rid of a half in a number? You're close. You don't add a half, you multiply by 2. So we want 2. If we multiply everything by 2, right? It's that same rule again. If you do the same thing to every one, the ratio is still constant. So 2 times that is 3, 2 times this is 5, and 2 times that is 2. Now our empirical formula is carbon, hydrogen, oxygen at 3, 5, and 2. So this is the empirical formula. Let's see. There it is. Now, how about the molecular formula? We're given the molar mass for adipic acid, 146 grams per mole. So what we need is the multiplier. So whatever we put in here to multiply will give us a molar mass of 146 grams per mole. Right? If we divide whatever this is by this empirical formula, and this is to 1, then we'll get that value. And if this, what is that value? I call it the empirical weight. So what's the empirical weight of this formula? Well, let's see, 12.01 times 3. And then 5 times 1.01 is 5.05, right? And then 2 times 16 is 32. 73.08. 73.08 per mole of that formula. Divide those two together, what do they give? About 2, right? 2. That's equal to N. So if we make this equal to 2, our molecular formula is actually C6H10O4. Okay, that's how you do it. Now, we had to assume 100 grams. Right? If you're actually given the mass in the ratio, then you can start from there. But if you're not given it, then just use 100 grams, and then you know parts per 100, that's 43, 49.3. All righty. Chemical reactions. We haven't balanced equations yet, have we? Okay, that's where we're headed then. So when you write, we've learned that, well, we're supposed to have learned the alphabet, right? Chemical symbols, element symbols, excuse me. Element symbols is the alphabet. Naming compounds gives us our words. Put this element, the symbols together. Now we're going to build sentences. And the sentences describe the chemical reaction. And they're always written in this form. Reactants first, something plus something yields products. Okay. This equation is balanced. How do we know? Because you have the same number of atoms of each element on the reactant side as you do on the product side. And we do that, we have the correct formula for each compound and each element. Right? C2H5OH is ethanol, the drinking kind. And O2 is diatomic oxygen, right? It's one of those elements, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. They're all diatomic in their most stable form at room temperature and pressure. So that's why we have oxygen as O2. Well, we can't change it. O2 is fixed in nature. We can't change it. If we need more oxygen atoms, we have to use a prefix or coefficient. That's what the 3 is for. Same thing for carbon dioxide. That formula is fixed. And water, that's fixed. So if you need more atoms of any of them on either side, you have to use the coefficient. So if we multiply 3 times O2, we get 6 oxygens plus the 1 that's in ethanol is 7. Look on the other side. We have 2 carbon dioxides, so that's 4 oxygens. Plus 3 oxygens from water, that's 7. We have the same number of oxygens. You can do that for all the elements. This equation is balanced. Now, that could be molecules, like 1, 3, 2, 3 is the ratio of molecules, or it could be moles. It works both ways. Right? Because you're ratioing the moles by Avogadro's number, which is the same for every one of them. So you can use it either way. The more practical way is to look at it as moles. Because if we see it as moles, now we're able to convert grams or masses to moles. And that's what you have to do in order to work stoichiometry from one side to the other. I'll show you that in just a minute. In the beginning, we're treating these chemical reactions as if they were 100% efficient. In other words, you start off with a certain amount of reactants, you get all of that mass back in the products. That's 100% efficiency. That's where we're starting. We'll talk about problems later. Okay. To balance a chemical equation, this is it in green letters, but it makes more sense when you actually see it done. Your book might say, once you write your compounds on the reactant side and the product side, then balance it by inspection. Look in brown and see if it says that. Most of them do. At least the older books do. That's a cop-out. They're evading the question. I need to know how to balance it. All right, so I'm going to show you a method, a starting method, and we'll blossom from there in the rest of this semester and into the second semester if you want to stick around. All right, these are helpful hints. One of the handouts, the third one over from the left, has all these helpful hints, and I'm going to use them as we look at various reactions. Okay. Let's see. All right. Rather than use this one first, I want to skip this one, come back to it. I want to go to the next slide. Here we go. All right. We have calcium oxide is a compound, and we're going to react it with carbon. And it's going to produce calcium carbide plus carbon dioxide. Okay? Any minors in the family? No? Old miners, like retired now? Okay. Ask them how they lift their way through the mines at night. If they're old enough, they use carbide lamps. You take these crystals of calcium carbide and put them in the reservoir in your lamp. And you add some water to it, and then you cap it off. And it decomposes into acetylene. And the acetylene goes up through the spout. You light it, and you have a light there. It lasts for hours. And then, of course, if you hit a pocket of methane or coal dust, then it'll all blow up. So that's why they got rid of the carbide lamps, and now they use insulated electrical lamps. Anyway, so this is our, did we write it correctly? Calcium oxide, +2, -2. Carbon is an element, pure element, right? Off by itself. Calcium carbide. In this case, calcium is 2+, and carbon is 1-. Okay. And carbon dioxide. Those are written correctly. Now we want to balance the equation. We know 1 calcium here, 1 calcium there is good. 1 oxygen, 2 oxygens there. 1 carbon, 2 carbons there. It's not balanced. So we're going to use my budget method. So what you do is you say, what elements do I have in this reaction? Put them down the side. We have calcium, oxygen, and carbon. That's it. How many do we have on this side? Calcium is 1. Oxygen is 1. Carbon is 1. On the other side, we have 1 calcium. We have 2 oxygens, and we have 3 carbons. Right, 2 there and 1 there. Okay, now you can start to balance, and notice that as we retally, as we add coefficients and we retally our totals, eventually we'll see equal numbers both sides. So you know instantly that you're balanced. Okay, where do we start? Well, where you don't start is with the free element. Save that one to last. Why? Because if you put a coefficient in front of that one, that's the only one you change. If you do one of these at the end and put a coefficient in front of that one, you change this one and that one. Now you have to go back and refigure everything else. So save the elements to last. Okay. All right, so we can't do carbon, let's do oxygen. We've got what? 2 oxygens there, we need 2 oxygens here. So that gives us 2 oxygens. It also gives us 2 calcium. Okay. So we can balance the calcium. We need 2 calcium. Okay, so that's 2 calcium. Now how many carbons do we have?
Oh, what you say?
5. Right. We have 2 times 2 is 4 plus 1. That gets me sometimes too. 5. Okay. Now, all we have to do is put a 5 right here. And we're balanced. Okay. That's my budget method. And it works for a large number of reactions. We're going to get into some reactions later where it doesn't work so well. Those are ones usually where you've got electrons moving. And you have to account for the electrons first, then you can do the rest. But this works for a lot of them, and it'll work for all the ones I'm going to give you on the next test. Or in the review document too. Okay, so, and we want the simplest whole number ratio. This is the simplest. You can't simplify it any further. That ratio is fixed. What can you divide by to give you a simpler value? Nothing. You got an even number, and you got 2 prime numbers here. Actually 3, because there's 1 here. Don't forget that 1. There's a 1 there. So if I ask you, what's the sum of the coefficients? It's 2 plus 7, 8, 9, 10. We don't write the 1, but it's there. It'd just be redundant to write it. Because if you've got the compound there, you got at least 1. Okay. So that's the budget method, simplest form. And we're gonna stick for the time being with whole numbers. Go for whole numbers. Later on, I think it's in the 2nd semester, we get to a position where we have to use fractions. And then you don't think of it in terms of atoms, you think of it in terms of moles. because you can have a half a mole easy, or a third of a mole, or whatever. But it's difficult to have a half an atom. All right, so let's go back and balance this one and use another trick. Notice in this equation, ammonium phosphate, calcium chloride yields calcium phosphate and ammonium chloride. Those compounds are written correctly. But notice that you've got polyatomic ions in here. If you have them in your equation, look to see, did those polyatomic ions remain intact from reactants to products? In this case, ammonium on both sides, right? It didn't break up. Phosphate on both sides, it didn't break up. If that's the case, you can use those polyatomic ions as balancing units. You don't have to break them apart. So that's what this is going to show you. There are your groups: ammonium, phosphate, but without the charges. Right? Charges just get in the way. Calcium and chloride. All right, so you do your initial tally. All right, you got 3 here, 1 phosphate, 1 calcium, and 2 chlorides. And then on the other side, you have 1 ammonia, you have 2 phosphates. Notice I forgot to subscript the 4 on the phosphate. It should be PO 4 subscript. There. Okay, now which one are you going to do first? Well, here and in the worked problems, if you look at the way I'm balancing equations in the worked problems, you'll have little numbers at the top. It tells you the order that I did at each step. If I just throw it there on the paper and without those numbers, you won't know what order I did. And the order is important. Okay, so the first step with that little red 1 is to put a 3 in front of the calcium chloride. That gives us 3 calciums because there are 3 calciums on the product side. It also changes the number of chlorides. So we retally right there, and then the chlorides. Now we have 6 chlorides. So we're going to go over second step and change the number of chlorides. And you need 6 chlorides. That changes 6 chlorides, and it also changes 6 ammonia. I should have done the chlorides first and then ammonia. Okay, so what do we got left? We got phosphate and calcium's good. How about phosphate? We got 2 phosphate. 2 phosphate. So for our third step is to put a 2 in front of the ammonium phosphate. That changes the ammonia to 6 and the phosphate to 2. And you can see, let's make it complete. You can see now we're balanced. All right, so let's skip this one because we already did it. All right, atoms are neither created nor destroyed. That's the one that remains that's the one that is no longer true. Oh no, that's one true, excuse me. I'm upside down. Atoms are neither created nor destroyed. That's still true. The rest of them are false. The number of molecules is conserved. No. The number of atoms of each element is conserved. Coefficients tell you how much mass? No, they tell you the numbers. Only the numbers. We're going to learn how to do the math, use the mass in just a minute. But first you have to have a balanced equation. When you're dealing with a stoichiometric problem, first thing you do is be sure that your elements and compounds in the reaction sentence are written correctly. That's why you have to know how to write and name compounds, because the word problem might give you the name of the compound in the reaction, and you got to be able to write it in order to write the sentence correctly, the chemical sentence, the reaction. Then once you've got that, about 5 minutes. Once you've got that, Then you balance the equation. And then once you've got the balanced equation, then you can do your stoichiometric calculations where you can relate masses of reactants and products. All right. So if you want, there's your flow chart. So for this one, let's see, how much more do I have in this chapter? Am I about finished with the chapter? At least chapter 4. I might just have to leave chapter 4 from a previous semester in the video section. All right. Well, we got a little bit to go. I think if you have to go, go ahead. I'm going to finish this so that there's continuity. P4, solid, plus O2. Oh, they went ahead and balanced it for us. That's nice. And that yields P2O5. That's a solid, I think. Yeah. If we start off with 6.25 grams of phosphorus, 6.25 grams, and we burn it in excess oxygen. No, we want to find out how much oxygen is consumed. If we consume completely the P4, how much oxygen is required? All right, there's a wall here. There's a wall there. There's a wall on the arrow and there's a wall on the plus signs. You can't get over that wall. You can't get under that wall unless you're moles. If you're grams, you're stuck. You have to convert to moles, to numbers, because these are related by numbers of things. So we convert this number of moles, number of grams, excuse me, to moles, grams per mole. So what's that value for P4? Right. We need phosphorus. Phosphorus is 30.97 times 4. Right? 28, 2 and 38, 38, 3, and 12. I think that's right. 28, 36, 38, 3. Yeah. 123.88. That'll give us the number of moles of phosphorus. 6.25 divided by 123.88. So let's see. Yeah, 3 significant figures. 0.0505. Now you can use it that way, or you can put it in scientific notation. This is the moles of P4. That's what you're starting with. Now you can move. So how do you convert moles of P4 to moles of oxygen? Coefficients. They tell you the ratio. For every one of these, you need 5 of those. So our conversion factor then is moles of P4, moles of oxygen. That cancels the moles here. And the ratio is 1 of these every 5 of those. So 5 times that value should be 0.2525, right? Moles of oxygen, if I did that right. Now that we know moles of oxygen, we can convert it back to mass. Right? All we need is molar mass of oxygen. Right? Moles, grams. 16. 16 times 0.2525. 4.04 grams. So this is 4.04 grams. Let's see if I did it right. Oh, I did something wrong. What did I do wrong? Oh. It's not 1 oxygen, it's 2. So it's 32, not 16. So it should be double that value. I'll just plug in a 2. Yeah, 8.07. 8.07. 7. Okay, how easy it is to make a mistake. All right, and that's 100% efficiency. This one coming up is a little more difficult, but if we break it down into pieces, it's not that difficult. So I'll show you what I mean. All right, here's the question. Methane, CH4, reacts with oxygen and air to produce carbon dioxide and water. Ammonia, NH3, reacts with oxygen in the air to produce nitrogen monoxide and water. Write the balanced equations. So we're going to do that first. CH4 plus O2 yields carbon dioxide and water. So if we use our budget method, if you do these enough, sometimes you can skip that tally procedure. They're really simple equations, but we're gonna work the whole thing through because this is new stuff for you guys. All right, we got carbon, hydrogen, and oxygen. That's it. 1 carbon, 4 hydrogens, 2 oxygens. Over here, we have 1 carbon, 2 hydrogens, and 3 oxygens. Okay. Notice we have an element here. Save that one till last. All right. Carbons are good. Hydrogens. Let's go to hydrogens. We need 4 hydrogens over here. 2 times 2 is 4. Now we have 2 plus 2 is 4 oxygens. Okay. So we need 4 oxygens. So I'll put 2 there. And we're balanced. Okay. Now let's balance the other equation. Ammonia plus oxygen. And let's put it about right here. Yields nitrogen monoxide and water. Okay. So let's tally. We got a nitrogen, we got hydrogen, and we got oxygen. We got 1 nitrogen, 3 hydrogens, and 2 oxygens. And over here we have 1 nitrogen, 2 hydrogens, and 2 oxygens. Does that look right? Oops. Yeah, that's right. 1, 3, 2. Sometimes you can check yourself. Just say, all right, 1 plus 3 is 4, 5, 6. 1 plus 3 is 4, 5, 6. So we accounted for everything. 1 nitrogen, 2 hydrogens, and 2 oxygens. Okay. So we got an oxygen here. We probably want to leave that one till last, which makes sense because it's already balanced. So we're going to have to go to hydrogens. So if we've got 3 hydrogens here and 2 there, this is one of those other tricks that I put in that helpful hints. When you got an element on this side that's odd and one that's even, and they're isolated. In other words, you don't have a hydrogen here and a hydrogen there and a hydrogen there. It's in one place here and one place there. Then the best way to balance them is to do both at the same time and cross multiply. So this 3 goes over here. And that 2 goes over here. Okay, now we need to retally. 2 nitrogens, 6 hydrogens, and 2 oxygens. Okay, on this side we have, let's see, hydrogens, 6 hydrogens, okay, and 4 oxygens. Correct? Okay, now we need to do nitrogens. We need 2 nitrogens here. That gives us 2 plus 3 is 5.
5 nitrogens, 5 oxygens. Oops, excuse me. 2 plus 3 is 5. Okay, let me see if I got those right. Let's see, that's 2 plus 6 is 8, 9, 10. 8, 9, 10. 2, 4, and 6 is 10, and 1 is 11. No, 3, excuse me. That's 12, 14, 16. It's 11. Okay, so something's wrong. I did something wrong here. 2 oxygens plus 3 is 5. 6 hydrogens, 11, 12, 13. 2, 4, and 6 is 10. Okay, something's not right. Two nitrogens, 6 hydrogens, 2 oxygens. It says 2 plus 3 is 5. So that's right. 5, 11, 13. 2, 4, and 6 is 10, and 3 is, okay, 13. Okay, we're good, we're good. So now we can balance. Okay, here comes another trick. We need 5 oxygens on that side to balance these 5. But how do you get 5? How do you get an odd out of an even? In this case, the trick is use an intermediate step. Use a fraction. If I say 5 halves, that's equal to 5 oxygens, isn't it? Right? 2 times 5 halves equals 5. Right? Okay. Now it's balanced, but we got to get rid of that fraction. Okay. So how do you get rid of a fraction? This ratio is fixed. 2, 5 halves, 2, and 3. So anything we multiply by the whole equation is going to preserve the ratio. So I'm going to multiply by 2. That gets rid of this fraction. Now it's just 5. This one's 4. This one's 4. And this one is 6. Okay? So it's 4, 5, 4, and 6 is our balanced equation. All right, I'm going to clean it up now. This is 4. That's 5. This is 4. And this is 6. Okay. So now we have our balanced equations. Let's see if they agree with the slides. 2, 2, 2. That one's good. 4, 5, 4, and 6. 4, 5, 4, and 6. Yep, that's good. Balanced equations. Okay, now the question is, what mass of that one? Let's just put it like this, question mark. What mass of ammonia would produce the same amount of water as 1 gram of methane? Okay. So look at it this way. The total mass of this water is equal to the total mass of that water. All right. So if we find out how many moles of that water, it should be the same number of moles as this water, right? Because they're the same molar mass. So if we know the moles of this, we know that then that moles is the same mass as this one. So that saves us a step. We don't have to calculate the mass of water. We just calculate the moles and then bring it down here and say, that's where we're starting from this one. So to find out the moles of water produced here, we have to change that to moles. So what's the molar mass of methane? Well, 0.01 for carbon, 4.04 for hydrogen, 4 times 1.1, 5061. So 16.05 equals the number of moles of methane. Which is 0.0623 moles of methane. Now we want moles of water. So we need to say, what's the ratio? Moles of water to moles of methane. Well, for every 2 waters, we have 1 methane. So we just multiply that one by 2. 1246 moles of water. All right, so we should have the same number of moles of water down here. 0.1246 moles. Now we want to find out how many moles of ammonia. Well, I'm going to work this direction. So we need ammonia on top and water on the bottom. Right? Ammonia is 4, water is 6. So 2/3 of that value, 4 times that divided by 6, is 0.0831 moles of ammonia. Now we're going to convert it to grams. So this is in the numerator. This will be in the denominator. So what's the molar mass of ammonia? Well, it's 14.01. And when we're doing molar mass, you don't use the coefficient. You only use subscripts. So we got 1 of these, and we got 3 hydrogens. 1704. So 17.04 times that value would give us 1.4156 grams of ammonia. And we can keep 3 significant figures, 1.42 grams. Okay. Okay. That calculates the moles of methane. That changes the moles of methane into moles of water. Now that we have the moles of water, we convert that into moles of ammonia, and then the moles of ammonia into grams of ammonia. Right there. Okay. So it looked really difficult, but when you break it down into its pieces and components, then the pieces aren't that difficult. You just fit them together. All right, now we're going to talk about limiting reactant. This is the reference I made earlier to reactions. At the beginning, we assume them to be 100% efficient. That is, when we do these calculations, these stoichiometric calculations, that tells us what the outcome would be, 100% efficiency. But that never happens. Actually, this is a topic, limiting reactants, that still assumes 100% efficiency. I was jumping ahead of myself. Limiting reactant is the reactant that runs out first. Why is that important? Because if one of the reactants runs out, the reaction stops. So we need to find out which one of the reactants is limiting. All right. This illustrates what we're talking about for a stoichiometric mixture. A stoichiometric mixture means you have exactly the right number of reactants and product, and of the two reactants, to give you product, and there are no reactants left. They're all gone. That's a stoichiometric mixture. And by the way, stoichiometric mixtures in the real world never happen. And there's one reason: experimental error. Your measurement error will never allow you to have exactly the right amount of each component. So this is theoretical, stoichiometric mixture. So we need 1 mole of ammonia, 3 moles of hydrogen. That's what this represents. There's 1 mole of ammonia, there are 3 hydrogen, and that gives us 1 mole of nitrogen, 3 moles of hydrogen, give us 2 moles of ammonia. Okay, this is an example of a limiting reactant. So which one is limiting? Well, who's left over? The nitrogen is left over. We have 2 nitrogens that didn't react. So that means the other one has to be limiting. Hydrogen is limiting. It runs out. All right. So for this limiting reaction is the one that runs out first. That's hydrogen. Which of the following reaction mixtures could produce the greatest amount of product? Each involves the reaction symbolized by the equation. All right. So if we got hydrogen and oxygen yields water, and A says if we have 2 moles of hydrogen and we have 2 moles of oxygen, right? How many moles of water will that produce? Well, if we look at this one, if we have 2 moles, how many moles of hydrogen are required if you have 2 of these? Well, the ratio is 1 to 2. So this will be 2 to 4. You need 4 over here, right? You don't have it. So hydrogen is limiting. And the most you can get out of this is 2 to 2, or 2 moles maximum. This is the limiting reactant. Once you find the limiting reactant, then you can do the ratio. 2 to 2, 2 to 2. Suppose we have 2 and 3. You got a similar situation. That one runs out first. You're only going to get 2 moles of water, and you'll have excess oxygen. What if we have 2 here and 1 there? That is a stoichiometric mixture. 1 gives you 2, 2 gives you 2. Right? This one is stoichiometric. D, 3 and 1. 3 and 1. This case, with 1 of these, you only need 2 of those, so you have excess hydrogen, and you run out of the oxygen. So the ratio is 1 to 2. You get 2 moles of water. And E, each produce the same amount. That's it. Each one of these will produce the same amount of product. Okay. Next, excuse me. There we go. Right, you can't just simply add the total moles of all the reactants and decide which reactant mixture makes the most product. You always have to think about how much product can be formed by using what we are given. So the foolproof way is to say, how much product will I get from this reactant? Say A plus B yields C. We say, how much will I get from here? Right? C possible from here. Then C possible from here with that amount. If all of it is used up. If all of this is used up, I get that much. If all of this is used up, I get that much. The least amount of C tells you which one is limiting. So if this is the least, that one is limiting. That's what we're saying. All right. Let's see. Okay, we got 2 more slides, I think. Percent yield. This is the way we approach inefficiencies in a reaction. In other words, you can expect to get, for 100% yield, how much do you get from that? And then you run the experiment, you isolate the product, and you say, how much did I actually get? That goes in the numerator, theoretical goes in the denominator, times 100, that's your percent yield. And your percent yield, if your percent yield is 100%, then something's wrong, right? Rarely does it go over 100%. Most often your percent yield is less than 100%. Sometimes a lot less. For various reasons. It could be your reaction conditions are not efficient. In other words, you don't get complete conversion. Your reaction could also be off in such a way that it produces side reactions. In other words, reactions that are not the one you expect. And that bleeds away product, reactant, so that you can't make a product. Or it could simply be isolation, right? When you have a reaction, if you've got any leftover reactant, you've got to isolate your product from that. Or if it produces side reactions that you know are going to happen, you've got to isolate the product that you desire. And then compare that to what your stoichiometry tells you you should be getting. Those are just 3 or 4 possibilities. Okay, for this last one, P4 6F2, P4 plus 6F2. Oops, I think that's a gas. Yeah, it's a gas. Yields 4PF3. Yes? Yep. Okay, we're going to combine several of the things we've learned already. The question is, what mass of P4? How many grams of P4 is needed to produce 85 grams of PF3? This is the actual amount that we're going to have. 85.0, yes, grams actual yield. If we know the reaction is 64.9% efficient. So percent yield equals, 64.9%. And that's equal to actual divided by theoretical times 100. Okay? This is the actual. So, before we can use this equation for our stoichiometry, we need to know what would be the 100% efficient amount of PF3. And for that, we need this equation. So we know this value right here is 85. Right? And that's equal to 64.9%. So theoretical would be over here. And then we put 85, that's grams, over 64.9% times 100. Yep. Okay, so now we just need to do a calculation. $85 divided by 64.9 times 100. 130. Let's do 0.97. Since all these calculations are going to be multiply, divide, we'll keep a few decimal places to avoid rounding error. So this is theoretical. Now we can work our way backwards. If this is the theoretical amount of PF3, we need to find out how many moles that is. So we can move over to this side. Right? So PF3, phosphorus is 30.97. And then 3 times 19. Okay. 30.97 is 87.97 grams per mole. 87.97 divided into 130.97 is 1.489 moles of PF3. Okay. So if we have 1.489 moles of PF3, how many moles of P4 does that represent? All right, so we can cancel these two. Right, moles, moles. The ratio is 1 of these and 4 of those. So we divide 4 into that value. 372, 0.3722 moles of P4. And now we want to convert that into grams. So what's P4 in grams? 30.97 times 4. 123.88. Multiply that times 0.3722. And we get 46.3 significant figures, 46.1 grams of P4. That's what we have to start out with in order to end up with an actual amount of 85 grams. Okay. And that should be the last slide. Yes.